Hello, and welcome to the video for the TI Precision Lab discussing electrostatic discharge, or ESD. In this video, we'll explain how ESD can damage semiconductor components. We will also give detail on internal ESD protection circuits that are included in semiconductor devices. Finally, we will explain how ESD performance is characterized so that the robustness of the device is understood. Many common items can develop a static electrical charge. Insulators are especially prone to developing large static charges. Some materials tend to become positively charged and others become negatively charged. Whenever two items with a charge imbalance are brought in close proximity, you can have a sudden flow of electricity between the two objects, called an electrostatic discharge, ESD. ESD can show up as a visible spark and often has voltage levels in the thousands of volts. From a semiconductor perspective, ESD is the most common way that devices are damaged. The table at the top of this slide lists some materials that generate significant static charges. Also notice that the static charge is dependent on the relative humidity. Lower relative humidity generates more static charge. The table at the bottom of the slide shows ESD discharge voltages versus human awareness. Notice that when you can see an ESD spark, the voltage is very large, at 8,000 volts or more. Different device types are susceptible to different levels of ESD voltage. Some devices, such as MOSFETs, are susceptible at very low voltages. We will see later that ESD protection circuits are used inside most semiconductor devices to enhance ESD robustness. The ESD robustness of a MOSFET can be improved from only 10 volts to thousands of volts with additional ESD protection. Let's look more closely at the typical way in which semiconductor devices are damaged by ESD. Consider a large ESD potential or voltage which is applied between the inverting input and negative supply pin of an op-amp. This places a large voltage from the gate to the source of one of the input MOSFETs, which can cause damage to the device. Keep in mind that the thickness of the MOSFET gate oxide may only be a few nanometers, making it very susceptible to this kind of damage. There are two main categories of ESD events for semiconductor devices. An out-of-circuit ESD event can occur to a loose device, that is, a device before it is soldered to a printed circuit board. Out-of-circuit events can happen during manufacturing, factory test, or the assembly process. In general, factory test and manufacturing processes are designed to minimize exposure to ESD. An in-circuit ESD event refers to damage caused on a fully assembled PCB or end product. In this case, the product packaging, product design, and the device's own robustness determine the ESD susceptibility of the product. The ESD protection circuits that are included in the device are intended to protect against out-of-circuit events. There are some general precautions that can be followed to minimize ESD damage to devices and assembled products. In general, these precautions use resistive materials to dissipate charge. For example, the anti-static wrist strap shown in this picture allows a controlled discharge of static electricity to ground. Typically, the impedance of anti-static materials is in the megaohms. Note that the anti-static bag, box, and work surface also contain resistive materials that are intended to slowly neutralize charge. During the initial development of a semiconductor product, the ESD robustness is characterized. First, a statistically significant sample of devices are fully tested using automatic test equipment. Generally, most of the datasheet parameters are measured during this automated test. Second, a specialized ESD test system is used to apply a simulated ESD pulse to the device. The specific characteristics of the ESD pulse are controlled by the test hardware. For example, the amplitude and ESD model can be selected. Various ESD models will be discussed later, but in short, the ESD model sets the capacitance, inductance, and charge of the ESD pulse to simulate a real-world ESD event. During the test, the ESD pulse is applied to many different combinations of device pins for a significant sample of devices. Also, different levels of ESD pulses are applied, for example, 1 kV, 2 kV, 3 kV, and so on. Finally, the comprehensive test is repeated on the devices. The ESD rating of the device is determined by the highest ESD level that all devices in the sample pass. This ESD rating is listed in the absolute maximum rating table of the datasheet. 3 different models are used to generate controlled ESD pulses. The human body model, or HBM, is first and the most common model developed for ESD emulation. This model attempts to emulate the ESD discharge that could occur when a human touches a microelectronic device. Typical HBM voltage levels range from 1 kV to 5 kV. The machine model, or MM, is also called the 0 ohm model because it simulates a very low impedance discharge of static charge to ground. The MM is meant to simulate a static discharge in a metal handler or automatic assembly equipment. The machine model has in most cases been replaced by the charge device model. The charge device model, or CDM, is designed to accurately simulate the test and assembly environment, for example, the static charge developed when a device slides down shipping tubes. CDM voltages are typically in the hundreds to thousands of volts. CDM currents are higher than HBM currents because the current limiting resistance is much smaller. Here we illustrate the ESD protection circuits commonly used on semiconductor devices. In this case, an op-amp is shown, but similar ESD protection is used on other types of devices. Remember that this type of ESD protection is intended to protect the device from an out-of-circuit ESD event. In other words, these structures are intended to protect the device during the test, assembly, and manufacturing process. They are also effective for ESD protection in unpowered systems, but they may actually cause issues such as latch-up in powered systems. The video series on electrical overstress will cover this topic in much more detail. 3 common structures used in ESD protection are the series resistance, steering diodes, and absorption device. The steering diodes turn on and direct the ESD pulse away from the sensitive circuit elements to the absorption device. The absorption device absorbs the energy of the ESD pulse and limits the voltage level to prevent damage. The series resistance limits the input or output current. Note that a larger series resistance offers more protection, but often degrades other key parameters such as noise or maximum output current. This practical limitation on resistance may affect the ESD robustness of some devices. Let's examine how the ESD protection structures work. In this example, an ESD pulse is applied between the non-inverting input pin and the negative power supply. In the real world, this could happen by improper handling of the device, for example, assembling a PCB on a non-static safe work surface. Notice for this example that diode D3 becomes forward biased and steers the ESD pulse to the absorption device. The absorption device is designed to limit the voltage and absorb the energy of the ESD pulse. Note that if the ESD pulse were applied to different pins, different diodes would turn on and steer the pulse to the absorption device. Also notice that the input resistance R2 limits the input current from the ESD pulse. A larger value of R2 will make the circuit more robust, but may introduce errors from bias current and noise, and may also affect frequency response. These specifications are meant to give a general idea of the ESD diode's performance. Actual diodes will vary depending on the device design and the process used. One key thing to notice is that the diode drop is about 0.7 volts with significant current. This diode is designed to take amps of pulse currents for only a few nanoseconds, as is typical with ESD pulses. However, they are rated for only 10 milliamps of continuous current. These diodes also have a reverse leakage current that may be less than a nanoamp at room temperature, but could be hundreds of nanoamps at high temperature. In fact, leakage current from ESD diodes makes up the majority of the bias current of CMOS devices. Finally, it should be noted that the ESD diodes have parasitic capacitance in the low picofarads. Here we take a look at the IV characteristic for the ESD diodes in two different op-amp ICs. Notice that at low currents, the forward drop is about 0.7 volts, and at high current, the drop increases to about 1 volt. Understanding the ESD diode characteristics will become useful when investigating electrical overstress issues in later videos. We previously discussed the absorption device only in a very general sense. The absorption device is a parasitic bipolar device that is formed vertically with regards to the substrate. Normally, this device is reverse biased so that no base current flows. As the voltage across the device increases, the collector to emitter reverse breakdown is approached. Increasing the voltage beyond the breakdown level causes a rapid increase in current. Collector current will increase until a point where a snapback takes place. Beyond the snap region, current again begins to rapidly increase. If there isn't another source of resistance in the transistor's path to limit the current, it can increase to the point where the thermal generation results in excessively high temperatures and transistor meltdown. Usually the emitter ends up spiking through the base and shorting to the collector, forming a permanent short circuit. The absorption device is designed to clamp the supply voltage during an out-of-circuit ESD event to prevent damage. Once the event ends, typically after a few nanoseconds, the absorption device turns on, since there is no power supply connected to the device. On the other hand, if the absorption device turns on for an in-circuit event, it will remain on and in a low impedance state until power is removed from the circuit. Thus, it is imperative that the absorption device is not allowed to turn on during in-circuit electrical overstress events. This topic is the focus of the next video series. The absolute maximum ratings given in a device datasheet describe the worst-case conditions that can be applied to a device before damage occurs. Maximum supply voltage, input current, and temperature are given. Notice that the maximum input current is given as plus or minus 10 milliamps. This is the limit for most devices and is based on the maximum continuous current that the ESD diodes can sustain. Also notice that the ESD ratings for the device are given in the maximum ratings table. In this example, the rating is 4 kilovolts for the human body model and 1 kilovolt for the charged device model. Different devices will achieve different ratings based on their performance during characterization. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content.